Okay, define and calculate integrals for polynomials. Good fun. Okay, so what is an integral? So this is actually easier to explain as, at first at least, is thinking of as an integral as just an antiderivative. So imagine we've got a function, and I'm going to call this my original function, so y or f of x. We know how to take a derivative, right? Bring the power down, bring it down the front, all the rest of it. Right, so that's y prime or f prime of x, depending on which system you're in. Right, if we reverse that process, if we anti-differentiate, right, instead of the power coming down, the power would go up. Okay, so my original now becomes what is sometimes called the primitive. So sometimes you'll hear it called the antiderivative, sometimes you'll hear it called the integral, sometimes you'll hear it called the primitive. They all essentially mean the exact same thing, it's just in the context of certain more technical stuff. Usually then they bicker about the name, but for us, all three will usually be perfectly fine. Cool, well, if you have a prime, that means you've gone down. In order to go up, you usually capitalize whatever the function name was. So y becomes capital Y, f of x becomes capital F of x. Beautiful. A little bit of notation thing, this curly thing, it's called summa. That just means to add up across. So it's kind of like sigma, except this is talking about an that's talking about an infinitely many infinitesimally small things, whereas this is talking about actual counting so much. So they both mean to sum up, but in rather different circumstances. Dx we've done before, so you can think of it as a small change in x, most of the time. Or depending on the context, you can read it as with respect to x. And I'll come back to that when we get there. So, I've written a whole bunch of stuff here. Okay. Capital F of x, so the primitive or the integral or the antiderivative, any of those, is this concept. So, this is just notation. All this means is, as far as you guys are concerned for now, is take the integral of this function with respect to x. So it means that treat x as the variable, which for most of the time you won't have a choice because there'll only be x's in there, but you could just as easily swap out all of these x's for t's or z's or whatever else have you. Cool. By the same notion, our original function is the antiderivative of the derivative, because if you anti-differentiate a derivative, you cancel yourself out, you end up back where you start. Almost, anyway, there's a slight little tweak to that, which we'll get to, but that's okay, that's a good general idea to have. And similarly, if I take the derivative of the antiderivative, I end up back at the original. So derivative and antiderivative are almost exactly the opposites of each other. There's only one small technical little glitch with that, which we'll get to very shortly. Some little shortcut rules that are handy to know. Just like with derivatives, if you've got a bunch of functions added together, you can take the integral of each of them separately. So if they're added or subtracted from each other, you can do each piece individually. If you've got a number multiplying a function, you can either do the integral with that number in there, or you can do the integral with the number on the outside. So this number, it just scales the whole thing. It doesn't actually interfere so much. It just tells you how big the size is, and that size doesn't get affected by the integration. Cool. Okay. Forget this plus c is here for a second. That's just to remind me to address it. Okay, so I've got x squared. If I take the derivative of x squared, I get 2x. If I take the derivative of 2x, I get 2. Right? So going down is deriving. If I went back up that list, that would be anti-deriving. So 2, if I integrate that, I get 2x. If I integrate 2x, I get x squared. Now there's one slight problem with all of this. If we say that this is our function, I could do x squared plus, say, 3. And if I derive that, the x squared will go to 2x, but the 3 will just disappear. Well, but when I integrate this thing, I have no idea what number I started with, because it disappeared altogether. If this was a 3, or a 7, or a 12, or whatever, pi, or 127 over 2,843, right? It doesn't matter what that number is, I lose that information. So there's one slight annoyance. When you integrate, you've always got to put on this plus c to just recognize that there could have been a number here that I don't know what the value was. It could have been anything. So you've got a plus c just to recognize that, oh, when I derive, whatever this number is, it will always disappear. So there may have been a number. It could have been 0, it could have been non-existent, but it could have been anything. So we put on plus c just to recognise there could have been some constant on the end here. Cool. Our general rule for integration is exactly as follows. So this is like the power rule, but in reverse. So if you start with ax to the n and we want to integrate it, well, the power has to go up by 1, so that becomes n plus 1. And then you're dividing by whatever the new power is. So a divides by n plus 1, and as always, plus c goes on the end. Beautiful. So let's try to integrate some of these boys. Alright, I'm going to write capital F of x. Okay. So I need the power to go up by 1. So this has to become x cubed. Okay, well, I end up with 3 divided by my new power, 3. Okay, well, this is just 1, so I end up with x cubed. That's nice. Because these are all split with pluses, by the way, I can split it up into separate stages. Cool. Plus, this thing, power goes up by 1. Alright, becomes 2. So I've got 4 over 2. Great. Simplify. 2x squared. Fine. This thing, power goes up by 1. Now that doesn't mean it becomes 5 squared. That means I've got this x that isn't here, right? Because I could do x to the power of 0, essentially. So now it becomes 5x to the 1. Well, that's just 5x. Brilliant. Now, last thing, whenever you do an integral, always plus c. Now, if you're wondering why I haven't done plus 3c, since I don't know what any of these are, I can just represent the sum of all 3 of them as this unknown number. Because I have 3 unknown numbers and I add them, I'm still just going to get some unknown number. So rather than writing C, D, E, I just write the whole thing as plus C. It just represents some number, whatever it is. Beautiful. Next guy, something slightly more complicated. Okay, we want to integrate this thing. Okay, power goes up by 1, so that becomes 6. Now you can do all this fraction stuff if you want, but it makes life a little bit easier if you're thinking smarter and faster. Cool, 12 divided by 6, well, that's 2. Now, a good idea when you're doing these, particularly if you're going to do a shortcut method, is just quickly derive it in your head and make sure you get the same numbers back. 6 by 2 gives me 12, this drops by 1 becomes 5, 12x 5. Beautiful. Minus. Okay, this thing has to go up by 1, so that gives me 4. This thing doesn't divide by 4, so it should be 5 on 4. Quickly derive this in your head, and make sure you get back to where you started. Cool. Next guy. Cool. Oh, well now I've got a fractional power. That's irritating, but we can still do the exact same thing. Add 1 to this. Okay, so it's not 3 on 3. Right? This is 1 plus 2/3, which would be 5/3. Okay, this becomes a little bit fiddly. You can do this in one stage if you're okay with the fractions, but rather than tempting fate, let's do it slow and steady. So I need 4 divided by 5/3. Okay, that's a bit chunky. I'll finish that off on the next line. This thing, okay, first thing, recognize that this is x to the power of a half. Okay, we've got to go up by a power of 1, so that's x and 3 halves. Our original coefficient was 1, divide by this. Okay, and as always, when you get to the end, plus c. Cool, this guy, that's all happy, don't have to change anything. This guy, that's as good as it's going to get, don't have to change anything. This guy, we can definitely neaten up, fractions, so 12 on 5, x to the 5 on 3. Plus this guy, well, that's just 2/3, x to the 3 on 2. Notice that that thing just flipped over, that's a good shortcut. And lastly, plus c. Brilliant. So that's integrating in a nutshell. Okay, well, there's some extra ideas we want to throw at this because if you're okay with deriving, integrating, at least for polynomials, very straightforward. It's the same thing, just in reverse. You just have to remember, add plus c on the end. Alright, well, the extra idea, and this is not obvious at all that this should happen, hence why I'm just going to tell you that it does, and you'll be like, oh, okay. So, I've got some function, doesn't matter what it is. So that's the blue line there. So that blue line is going to be f of x, okay, which I should probably label. Let's say I wanted to know what the area is underneath that curve between x values a and b. Well, it turns out that integration allows you to do this in a relatively straightforward manner. So this area is equal to the definite integral between a and b for this function. So, what's a definite integral? A definite integral is an integral which then you have a start and a finish to, which just means that you have the integral at the endpoint minus the integral at the start point. The difference of those is the difference in this area. That's not the only way to think about it, but it's a very common way to think about it because it allows you to have some tangible link in your head as to what you're doing and what should or should not happen. So let's run through an actual example of this. So I want the area between x is 1 and x is 3 for the function x squared. Okay, well, the area will equal the integral with respect to x, because we're moving in the x direction, for the function x squared between the values of low to high 1 to 3. Beautiful. Okay, well, what does that equal? Where are we going to do this? Yeah, we'll do that. Okay. Integral of x squared. Okay, well, power goes up by 1, divide by the new power, so that's 1/3. Now, what was my integral, my definite integral, what was it between? It was between 1 and 3. So that little sidebar just means do this between these numbers, or these values. Okay, so now I've got 1/3 of 3 cubed minus 1/3 of 1 cubed. Great, well that's 27 divided by 3 gives me 9 minus 1/3 on 3, so what do we get? 26 on 3. So that area happens to be 23/3. Now, if you're asking about units, that's fine. It depends what your units of your axes are in. For a lot of the time, you're not even going to have units. It will be a dimensionless quantity. It's just whatever this unit is multiplied by this unit. So if this was meters and meters, then this would be meters squared. If it's a mix of units, then you're going to have a bad time, but you can still figure that out. For the most part, though, it won't require a unit. It's only in application questions that usually turns up. Okay. Next idea. Cool. So anyway, just to be clear, this definite integral is the same as an indefinite integral, but it's just got this extra step at the end where you just sub in values and minus away. Cool. Next thing is when you've got what are called initial conditions. So I've got the derivative function f prime equals this. So I know how this thing changes over time. I know its derivative, but I want to find its original. This part here says that the original when x is 3, y is 5. Okay, so this part here is called our initial conditions. Very commonly, this will have times 0 or something, so that's why it gets the name initial conditions. But basically, it just tells you what's happening for the original function. Okay, well, I've got the derivative. I want the original function. Okay, so the original function would be the integral of this thing. Well, hopefully you've noticed straight away, we haven't learned how to integrate things that are multiplied together. So hopefully we're going to go, oh, actually I should switch this out. What's this? I'll do this in red. So this function, cool. I should expand this out. Cool. Beautiful, okay. So f of x equals the integral of this thing. Well, it's a whole lot of things separated by plus and minuses now, so I can do it piece by piece. Great. Power goes up by 1. This divides by new power. Power goes up by 1. This divides by new power, so 2 divided by 2, which is just 1, so I don't have to worry about it. This goes up by a power, so that's 3 to the power of x. And after you integrate, plus c. Now, you'll notice that I did plus c here, but not here. Why is that? Well, if you imagine for a second I put a plus c in here, I'd have plus c there, and then minus another plus c here. So whenever you have a definite integral, the plus c always cancels itself out, so you don't have to worry about it. Which was an oversight on my part because I just did it out of habit. But it's perfectly valid. Cool, alright, so we've got this. Great, we're almost there. We're just missing this part of the function. Well, this is where the initial condition comes in. So we can say, great, f of 3 equals 5. Well, that means all of this, when x is 3, must equal 5. So 1/3 of 3 cubed minus 3 squared minus 3 plus our unknown c. Brilliant, okay. So we've got 5 equals, this thing becomes 9, this thing also becomes 9, this thing also becomes 9. They won't always be all 9s. So I've kind of cheated a little bit to make the math nice and easy to follow. So these two kill each other, add that to the other side, get 14 equals c. So therefore, oops, that's terrible, therefore f of x equals 1/3 x cubed minus x squared minus 3x plus 14. And that's that. Now, a bunch of this won't actually appear in 17e. I'm just trying to give you as many pieces as possible. So this will, that won't, but this allows you to at least give you a thought of why you're doing what you're doing, or at least give you a geometric interpretation of the algebra, which can help. There is every possibility that this will cause some difficulties at some point. That's totally fine. Just email me whenever you have troubles. A little bit of perseverance does go a long way. For now, that's 17E out of the Year 11 methods book. Good luck to you. Cheerio.